Hey everyone, welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're diving into Lesson 10 of the Arduino Uno R4 Minima Ultimate Training Series, focusing on array programming and musical tones with a piezo buzzer. For today's lesson, you'll learn how piezo buzzers work and how different frequencies can produce musical tones. Aside from this, the highlight of our discussion is for you to understand the importance of using arrays in organizing your data to deliver efficient Arduino codes. Throughout the discussion, you'll see how looping and arrays are used to simplify hard-coded data, multiple variable declarations, and repeated codes. At the end of this lesson, you'll perform a challenge activity that allows you to write a program that plays your favorite song using arrays and a piezo buzzer. In addition, the speed of the song can be adjusted through the use of a potentiometer. And as always, before we start, I'd like to extend my sincere gratitude to SunFounder for sponsoring this course and enabling everyone, especially beginners, to embark on this comprehensive educational adventure. Also, if you're new to this channel, I want to let you know that I am using the SunFounder Arduino Uno R4 Minima Ultimate Sensor Kit for all my video lessons throughout this series. This is a great tool to learn the new Arduino Uno R4. This kit includes a lot of sensors that we're going to use for our future lessons on the Internet of Things. So, if you are still looking for a learning kit, I encourage you to please check this one out. This is available on the SunFounder website as well as on Amazon. The links are provided below. So now, let's begin. For this session, you need the following materials: a 1 kilo ohm current limiting resistor and 1 LED, a passive piezo buzzer, or the SunFounder passive piezo buzzer module, a 10 kilo ohm potentiometer, and of course, a breadboard, some connecting wires, in your Arduino Uno R4 Minima. In lessons 8 and 9, you've learned how to control RGB LEDs using pulse width modulation. Now, what is a piezo buzzer? And why do we have to use one? A piezo buzzer is a type of electronic device that is used to produce sound like a bip. It can generate tones that you can use to produce song melodies. Piezo buzzers are commonly used in alarms, warning devices, automobile alerts, computer sounds, telephones, children's toys, and game consoles, just to name a few. There are two types of buzzers based on control methods: active and passive. Active buzzers are the simplest to use because they have a built-in oscillator, which means they can produce sound right away once connected to a power supply. The main downside of active buzzers is that the frequency of the sound is fixed and cannot be adjusted. Therefore, you cannot generate different tones to produce song melodies using these buzzers. Passive buzzers, on the other hand, do not have built-in oscillators, which means they require some sort of external signal to produce sounds. In a way, they are a bit more complex to control as compared to active buzzers. But the main advantage of passive buzzers is that they can be programmed to emit a wide range of frequencies to produce musical tones. A passive piezo buzzer relies on a piezoelectric element inside it. Piezo is a Greek word which means pressure or push. And as the name implies, a piezoelectric element creates a small amount of electricity when it is pushed, squished, or receive vibration. And oppositely, if you apply a voltage to a piezoelectric element, it will slightly flex or vibrate. And if you cause a piezoelectric element to vibrate several thousand times a second, it will produce an audible sound. The pitch or note produced by a piezo buzzer depends on the number of vibrations per second the piezoelectric element emits. This is measured in hertz, based on the number of cycles per second, commonly known as frequency. For example, a frequency of 3 Hz means that there are 3 cycles per second. A frequency of 10 Hz means that there are 10 cycles per second. And if we apply this 10 Hz oscillating signal to a piezo buzzer, it means that the piezoelectric element inside it will vibrate 10 times in 1 second. So, passive buzzers require a PWM signal to produce sound. Ideally, a 50% duty cycle should deliver the loudest. 50% means equal time for the high and low signals. The duty cycle can be adjusted to programmatically increase or decrease the volume it generates. For now, we're not going to discuss that. Instead, we will focus on producing different notes or pitches, which means we are going to apply different frequencies to produce different notes. And with that, we can use any digital pins of your Arduino Uno. It doesn't have to be a PWM pin to generate different frequencies. To understand what I meant, let's implement this simple circuit diagram where we have one LED and a 1 kilo ohm current limiting resistor connected at digital pin 8. Before we connect a piezo buzzer to produce sounds that we can hear, I want you to see them first. Now, in our sketch, we can have a program that sends alternating high and low signals several times a second to pin 8. So first, I'll define buzzer pin at pin 8 and set it up as output. Now, for example, I could use the digital write function to alternately send high and low signals several times a second to emulate a 50% duty cycle of a certain frequency. Now, let's say I want to produce 4 Hz. I could write 4 sets of these alternating high and low signals within the period of 1 second. And as you notice, I use a 125 millisecond delay so that each cycle consumes 250 milliseconds. Then, repeat this 4 times and we consumed 1000 milliseconds. It means that we have 4 cycles per second or simply 4 Hz. So, I'll upload this sketch. And as you can see, the LED blinks 4 times per second. Well, this approach is not very encouraging, especially if we are going to produce a much higher frequency. Just imagine, if you will generate 500 Hz, that means you'll have to duplicate this code 500 times. And then, divide all the delay values so that it adds up to 1000 milliseconds in total to produce 500 cycles per second. Well, the good thing is that the Arduino library provides us with a function that we can use to easily generate a range of frequencies to a specified digital pin. The tone function can generate a square wave of the specified frequency at 50% duty cycle on a given pin. This function accepts at least 2 parameters. The first parameter is the digital pin, and the second parameter is the frequency. So, this code should produce a similar result. I'll upload this sketch and verify the result. And as you can see, the LED also blinks 4 times per second, similar to our previous program. Although the output looks identical, the tone function implementation is different. This function is non-blocking, which means it doesn't block or stop other codes from executing while it continuously generates a square wave of the specified frequency. For example, if I generate 659 Hz, I'll upload this code first. And then, I'll replace this LED with a piezo buzzer. Note here that even though passive buzzers have polarities, you can connect their pins in any orientation. So now, we should be hearing a continuous sound being produced at this frequency. Well, the volume is a bit low. I can hear it, but my microphone can hardly pick up the sound it generates. So with this, I'll replace it with a piezo buzzer module. Now, this module includes additional circuitry comprised of a transistor and resistor to produce a more audible sound. Thus, it requires both the VCC and the ground to be connected using this module. And as you can hear, this is how 659 Hz sounds in a piezo buzzer. And this is going to play continuously until the no tone function is called. The no tone function accepts one parameter, which is the pin number. So for example, if I want this 659 Hz to play for only 125 milliseconds, I need to put a delay before calling the no tone function. This should turn off the sound. And then, I can have another delay to specify how long the no tone is going to last. Say, I'll turn off the sound for 1000 milliseconds before it loops back. And I'll upload the code and verify the results. So, as you can hear, we have a nice short beep sound that loops every 1 second. Now, if you're musically inclined or at least know something about notes, like the key of C, D, E, F, G, A, and B, you could start playing around with different frequencies and perhaps compose some melodies out of it. However, you can always refer to dozens of websites that present notes and their corresponding frequencies. For example, the one that we just played, 659 Hz, is note E on the 5th octave. So, let's try producing a simple musical tone. I'll duplicate this block of code 5 times. And then I'll play around with the delay values so that some notes play a little bit longer than others. Also, I'll change some frequencies. I'll make this 523 Hz, which is note C on the 5th octave. Also this one, I'll make this 784 Hz, which is note G on 5th octave as well. And finally, I still need this 1 second delay before looping back to repeat playing the same melody. So, I'll upload the code and verify the results. And we were able to produce our first melody. Now, you probably realized that even though we've used the tone function, this code structure is not going to be very efficient in the long run. If we are going to complete this song, we'll probably end up having several hundred lines of code because we have to duplicate these 4 lines of code just to add a single note to play. So, let's start simplifying this one a bit. The tone function also accepts a third parameter, which is the duration of how long the tone is going to play, in terms of milliseconds, before it stops, just like calling the no tone function. So, if I put this 125 millisecond delay as a duration parameter, we can remove this no tone function call here to simplify this code a bit. However, I will not be deleting the delay function call here because if we do, it will execute the next code immediately, even if the tone is not yet done playing. So, if the next line of code is another call to the tone function, that tone is played right away. Remember that the tone function is non-blocking. Now, regarding the delay, I'll add these 2 delay values and place them in just a single delay function call. The reason is that if note E5, for example, plays for a 125 millisecond duration in a non-blocking way, this delay function gets executed immediately as well. So, putting a delay value that is exactly the same as the duration value allows us to hear the entire note. And then, the excess delay is used to pause the code execution without a tone before playing the next tone. In this case, we will hear note E5 playing for 125 milliseconds and then a pause with no sound for 35 milliseconds. And now we can apply the same approach in simplifying the rest of the codes. I'll upload the code and verify if it still plays exactly the same. it works exactly as it is. Now, even though we have simplified this a bit as compared to the previous code, this current code structure is still not scalable. We still have to copy and paste several lines of code if we are going to add more nodes to play. This will still produce a lengthy code in the long run. Eventually, it will be very hard to read, update, and maintain. And with that, I'll introduce you to the concept of array. To illustrate this concept, let's investigate our current program structure. Notice that these codes look almost identical except for the hard-coded values that we pass to the tone and delay functions. So why don't we use variables for all these values? Well, let's try replacing these hard-coded values with variables. For example, the parameter frequency is of type unsigned int, so I could declare 6 variables of type unsigned int to store these 6 frequency values. And then, the duration parameter is of type unsigned long, so we'll have to declare another 6 variables to hold these 6 duration values. And finally, we need to declare 6 unsigned long variables to hold 6 delay values. Now, all we have to do is to replace these hard-coded values with our declared variables. Well, this is tedious and please bear with me for a while and we'll get there soon. Okay, now, as you noticed, instead of shortening our code, it has increased. And in this case, using variables seemed to be counterproductive. The reason why I showed you this is for you to appreciate what we are about to do next. We are going to use arrays. When you reach a point where you need to declare multiple related variables just like this, think of arrays. So, what is an array? An array is a kind of data structure used in programming by which it allows programmers to use a single container that holds multiple data in it. It is a structure for collecting similar data types stored at contiguous memory locations. So, to illustrate this concept, instead of declaring 6 delay value variables like this, we could just simply declare one array that could hold 6 delay values. It means we will just be maintaining one variable name instead of 6. So, to declare an array in Arduino, you put a square bracket at the end of the variable name. In this case, I'll call it delay values, with S as in plural, just a convention that it holds multiple delay values. Now, C language has different ways of declaring and initializing an array, but one of the simplest ways is to use a pair of curly braces after the equal sign, and then specify all the values you want your array to contain. So, I'll use these values, and these values must be separated by a comma. Now, I'll do the same for the frequency and duration variables. So, I'll declare and initialize an array called durations with the values 125, 250, 250, 80, 250, and 500. And then, I'll also declare and initialize an array called frequencies with the values 659, 659, 659, 523, 659, and 784. So now, I can get rid of these 18 individual variables since we already have 3 declared arrays. But the question is, how are we going to use this? We can access the individual array values or elements through an index. So what is an index? An index is just a number used to indicate the position of an element in an array. Array in C language uses zero-based indexing. This means that the first element inside an array can be accessed at index 0. And then, the second element can be accessed at index 1, and the third at index 2, and so on. So, to access individual elements inside an array, we need to specify the index inside the square bracket after the array name. For example, to access the first frequency value, I'll write frequencies index 0. To access the second frequency, I'll write frequencies index 1. For the third frequency, it should be frequencies index 2, and so on. Now, we can do the same for the durations array and the delay values array. Now, I guess you're wondering how in the world this code is considered simpler than the previous one. Well, actually, it is not. But this current code structure can now be simplified with the use of a loop. Since we no longer use hard-coded values here, these 6 code blocks look almost identical except for the index values. So, if we can just create a loop with a variable that starts with 0 and is incremented by 1 for every loop until it reaches 5, we no longer need to have these 6 identical code blocks. We just have to retain 1. And then, replace these index values with a variable. Think about this for a second. So, I'll remove the rest of the codes and then enclose this remaining code inside a for loop block. In our for loop statement, I'll initialize an integer variable I to 0 and then checks if I is still less than 6. This is the size of our array. We have 6 elements inside, stored at index 0 up to index 5. And then, I++. Now, instead of using a hard-coded value of 0, 1, 2, 3, 4, and 5 inside this square bracket, we use this variable I. So, it starts at 0, which is the first element, and then, each time it loops back, it accesses the next element in the array until it reaches the last element at index 5. Now, this code is way shorter than before. So, let's upload the code and see if it works. And it works exactly as it is. The main difference is that this is now more organized and scalable. It means that we can implement changes in our code to grow or add functionality easily. For example, I can easily put additional frequency values here to improve our musical tone. I'll do the same for the durations, and of course, for the delay values. If we're going to add these notes using our previous code, it is going to be a lot of work. Here, we just have to update these array values and we're good to go. Now, there's one thing in our current code that we need to modify to handle the changes in our array size dynamically. Notice that we use a fixed hard-coded value here of 6 since we have an array size of 6 elements previously. However, since we've added several elements to our arrays to accommodate more notes, our array size is now 24. So, to make our code more flexible, instead of changing this to a fixed value of 24, I'll compute the array size on the fly, so that we no longer have to change this every time we need to add or remove notes in our array. To compute the array size, we use the sizeof operator. The sizeof operator calculates the size that a data type occupies in the computer's memory. In this case, if we use the sizeof operator to compute the size of the frequencies array, it will give us 96 bytes. Why is that? Our array has 24 elements inside, And each element consumes 4 bytes because they are of type int. So, 24 elements times 4 bytes each is equal to 96 bytes of total memory being consumed by this array. But this is not what we want. We only need 24 loops for the 24 elements. With that, we need to divide the result of this by 4 bytes. However, I'm not going to put 4 here as a fixed value. Instead, I'll use the sizeof operator again to get how much memory an int data type occupies. And this will give us 4 bytes. So, 96 bytes divided by 4 bytes gives us 24. And this is how we can dynamically compute for an array size. So the next time we update the array elements and the size changes, this condition dynamically gets updated. Now, let's upload the code and test the result. And as you can hear, we are now playing a slightly longer version of the Super Mario theme song. Speaking of efficiency and scalability, we can further improve this program. Although you can hardly notice at a glance, but there is a strong relationship that exists between the note durations and the delay values. These two dictate the tempo or rhythm of the music. If you can see the pattern, the delay value is usually 30% bigger than the duration. Let's try to compute some. 125 times 1.3, that's 30% increase, gives us 162.5. And this is very close to 160. 250 times 1.3 gives us 325. And this is an exact value. 80 times 1.3 gives us 104. Again, very close to 110. And then let's try 500 times 1.3. It's equal to 650. Again, this is an exact value. So, as you can see, we can simply remove this delay values array and just base the delay value on the duration values multiplied by 1.3. Thus, we can save memory space. But wait, there's more. The note durations can also be computed as set of standard values. And we can use a smaller number here that's a lot easier to recognize and play around with. What do I mean? Try dividing 1 second or 1000 milliseconds by these note duration values. For example, 1000 divided by 125 gives us 8. This is an 8 note. If we divide 1000 by 250, we can get 4. This is a quarter note. So I can replace all this with much smaller values. And then, to compute for the actual note duration, I'll declare a local variable note duration and then take 1000 milliseconds divided by the individual duration value. Now, I'll replace this with the computed note duration. Similarly, I'll replace this delay value with the note duration multiplied by 1.3. So, I'll upload the code and verify the result. And it sounds great. Now, this code is more efficient and scalable than the previous, because now we can easily adjust the tempo or the speed of the song by simply multiplying these duration values by a certain fraction. This should increase or decrease the note duration. For example, if I want a tempo to be a little faster, say 20% more, I'll multiply this by 1.2. So, I'll upload the code and verify the result. And it works. Let's try another example. If I want the tempo to be a little slower, say 20% slower, so I'll multiply this by 0.8, and then I'll upload the code and verify the result. And it works as expected. For your challenge activity, I want you to modify this program so that it allows the use of a potentiometer to adjust the speed or tempo of the song. Much better if you can use a different song of your choice. So, by rotating the potentiometer counterclockwise, the tempo of the song is reduced. On the other hand, rotating the potentiometer in a clockwise direction increases the tempo of the song. Again, thank you so much for joining me in this lesson on arrays and playing musical tones with a piezo buzzer. For our next lesson, you'll learn how to control servo motors. If you found this lesson enlightening, don't forget to hit the like button, subscribe for more knowledge-packed sessions, and ring the bell to stay updated. So, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!